Okay, hello. So I'm Michael Ernstinius, or Ernst, and I'm here to talk to you about the intersection of programming language design and programming by voice. Um, so when we think about voice interfaces, we tend to think about casual convenience interfaces like voice assistants like Siri or Alexa. Um, and these are, handy for doing things without your hands. But when we think about doing, expert, serious stuff on a computer, we tend to imagine somebody using their hands, perhaps using a keyboard and mouse, which is standard for programming, maybe using a specialized controller for gaming or a stylus for art, but in any case, using your hands. And so there's this sort of blank area, which is in our collective imaginations of how do you use voice for as a power user um, to do something like programming. And probably the only thing that springs to mind for this is using voice for dictation, which seems like a fairly natural fit, right? You're using voice to do what voice is about, language. Um, so I'm in particular going to explore how we might have a voice interface for programming, or not how we might, how we in fact do presently. And your first question might be why? Why would you try to do that? And for me, the reason is RSI. I cannot type for more than about 1 hour a day without being in pain the next day. Um, so for me, it's not not really much of a choice. Um, for some people, there are various things that can resolve their RSIs: therapy, exercises, sometimes even surgery. But for some people, RSI doesn't go away so easily. So the talk outline is first I'm going to give you a few demos to just to familiarize you with what it looks and sounds like to code by voice and with some of the details of the tool I use, which is called Talon. Then I'm going to talk a little bit about how this all works um, behind the scenes. Then I'm going to start generalizing and talk about the challenges of voice as an interface and what makes it difficult to voice code. And then I'm going to begin to speculate a little and talk about how this might apply to the design of programming languages and programming language tooling. So let's get right into it. Focus Emacs. So the first thing I'm going to show you is how to spell, right? And we're going to learn our ABCs with Talon. Um, and the reason why this is important is sometimes in programming, you just need to press particular keys in a particular sequence, and there's no getting around it. And so Talon allows you to do this by assigning each letter of the alphabet a word. So for example, if I want to type this sentence, I would go like so. Made air red yank space, harp air drum space air space look sit trap trap look each space sun harp each pit space whale harp odd sun each space fine look each cap each space whale air sun space whale harp sit trap each space air sun space sun near odd whale. So as you can see, if you practice, you can actually get reasonably fast at this. It's not as fast as typing, but it's a good substitute if you really need to enter a specific string of text. In this case, obviously, it would be easier to just speak the text, which you can also do. But we'll see some more practical uses of this in the next demo. Switch word fib, slap. So now I'm going to write two very common example programs, beginner programs, combined together, Fibonacci and FizzBuzz. Function fib, near push, air assign 0, push, bat assign 1, push, state for in, under tail func range near finish decal, air spam bat assign bat spam air inner plus bat, push, state if air op mod 3 is equals 0, logical and air op mod 5 is equals 0, push, func print make string smash fizzbuzz, push junk, north tail left second scratch, smash fizzbuzz, south, state else if air op mod 3 is equals 0, push, func print, make string fizz, left zip, push junk, state else if air op mod 5 is equals 0, North, junk third, sit fine, join lines. Finish decal. Func print, make string buzz. Push, junk, state else. Func print air. Push, junk, state return, bat. File save. Split wide. Run Python. Python load file. Dexter word fib slap. Word fib round 20 slap. Talon sleep. Okay, so that was Fibonacci fizzbuzz. This is a fairly standard way to calculate the Fibonacci numbers. You just iteratively add things up, and at each step, we print fizzbuzz if one of the variables is divisible by 5 and by 3, fizz if it's divisible by 3, buzz if it's divisible by 5, otherwise the number. And you can see we get the Fibonacci sequence with some fizzes and buzzes in it. So how did this work? How did the tool I'm using, Talon, understand the things I said and turn them into code? Focus document. The very rough picture of how Talon works, and you can see it's rough because you can see all this white space that I've left under it to complicate the picture later, is there's a speech recognition engine that takes the words I'm saying, the sound, and turns them into a string of text, a sequence of textual words. This gets fed into a command parser. This then causes some scripts to get run, and these talk to our operating system to do things like type into our editor. So the speech recognition engine, I don't know a lot about. It's machine learning, so I'm not going to talk a lot about that. The operating system is a subject too large to handle in this talk, so we're mostly going to talk about these middle two things. How did these work? What are the available commands? What determines what the commands are, and what determines what they do? Focus Emacs. Split clear switch word demo. Slap. The answer to what determines these things is you do. Talon does not ship with a canned set of commands. Every command in Talon, every voice command, is defined by a user script. And so I've opened a Talon file in my user script directory, and well, let's define some commands. Phrase hello Santa Cruz over, declare string phrase hello from Talon over, bang. Push, file save. Hello Santa Cruz. So as you can see, I just defined a voice command. We can also have voice commands that do somewhat more interesting things that might be more useful for text editing or program editing. Clear line. Phrase please delete this line over, declare, func key, word home space, word shift dash word end space, word delete. File save. Please delete this line. Undo that. Slap. So what's going on here is if I say please delete this line, it presses the keys home, which goes to the beginning of the line, shift end, which selects until the end of the line, and then delete, which deletes the selected text. So that's an example of how you could build a command that's actually useful if you give it a better name than please delete this line for voice editing. Commands can also be parameterized. So let's look at an example of that. Slap, run multiply, angle word number, write padded by, angle word number, tail declare string curly, word number under 1, inner star, word number under 2. File save, push. Multiply 3 by 4. Slap, multiply 12 by 12. So here number is a placeholder for a sequence of words corresponding to a number. And on the right-hand side, we type the result of multiplying those two numbers together. So this is sort of a quick demo of how you might define commands in Talon. And almost all of my ordinary commands are defined like this. For example, I have a file full of commands for Emacs. Switch word Emacs, slap. And here you can see, for example, the definitions of the commands you saw earlier, which ran Python and loaded a file into the Python REPL. And you can see other commands to quit Emacs, save buffers, and do various other things. And this file is pretty full of commands. I use Emacs quite a bit. Focus document. So what's going on here is that there's a little domain-specific language in .talon files for defining Talon voice commands and for defining what happens when you run them, when you speak them. And so I want to focus in on this little domain-specific language. So we have a domain-specific language, the .talon files, that itself defines another language of voice commands by giving its productions, its syntax, giving the voice commands themselves, and defining the effect of these commands when executed. In other words, their semantics. So I'm a programming language researcher, and this sets certain wheels spinning in my head. Right? I start thinking, what useful things pop out if I treat Talon as an implementation of a programming language? Or more specifically, what Talon is doing is similar to something you might call a parser generator, where you give some parsing rules and their associated actions, and it parses some stuff for you. And this is a useful angle, but it's not really a normal parser generator, is it? For one thing, it's taking speech, but even ignoring the fact that it takes speech rather than text, there are some unusual constraints on Talon's implementation. For one thing, as we saw, it is live. I didn't have to run a compile step. I just changed my files, saved them, and the commands were immediately available. Okay, that's nice. It also needs to be error tolerant and ambiguity tolerant. So what do I mean by that? Focus Emacs. Switch word demo slap. North, delete 2 lines. Delete line. Push up second. Deli second. North second. Push up. Okay. What I mean by error tolerance is if I just jam on my keyboard a bunch, then Talon is still going to work. File save. Go bottom. Multiply 3 by 4. Multiply 12 by 12. And you might not be impressed. You might think, well, it just noticed that the file was garbage, and so it kept the previous version of the file and didn't override those commands. But that's not actually what's going on. Leap star, cap deli plus. File save, south push. Multiply 3 by 4. Slap. Multiply 12 by 12. File save. Multiply 13 by 123. So I just changed it to add 2 numbers, and this change took effect, even though all this garbage is in this file. The reason is that this DSL is specifically designed to have a very simple syntax, and its parser is robust to parse errors. It can deal with parse errors and keep parsing to find the commands that are valid, that are correctly formatted. And this is really useful. Admittedly, mashing on your keyboard is not a thing you're likely to do, but it means that if you make a typo in one command, it doesn't affect the rest of the commands that are valid in your Talon files. And here's a scenario where this might actually happen. Let's say you're keeping your user script directory under version control using Git, and then you perform a Git pull without thinking too much about it, and you get a merge conflict. Suddenly, all of your files are going to have little merge conflict markers in them. And this is going to make the syntax be incorrect. But any file that doesn't have merge conflicts in it will still work fine. And even the commands in files that have merge conflicts in them, if they're not part of the conflict, they will work fine too. So because Talon is so resilient, a lot of things that might be an opportunity to shoot yourself in the foot are no longer foot guns. And this is important because Talon is, if you can't use your keyboard, your primary interface to your computer. And if it stops working, you're put in the position of not using your computer, or maybe causing yourself a bunch of pain to try and fix it. So it's really important that it be robust to errors like this. I also talked about it being robust to ambiguity. So let's give an example of that. Delete 3 lines. Push up, run hello, angle, word phrase, write, declare, string, word hello, spam, curly word phrase. Push file save. Hello Bob, slap. North. Hello Bob, slap. Hello Mary, slap. Hello Santa Cruz. So this is a somewhat contrived example, but here you can see hello phrase, except hello followed by any sequence of words. And it just prints, hello, comma, whatever you just said. But there's also a command hello Santa Cruz. So when I say hello Santa Cruz, which one of these should fire? In a normal parser generator, this would be a grammar ambiguity, and it would reject this. It would tell you, I'm sorry, I can't help you. You need to make your grammar unambiguous. But Talon soldiers on, because if you have a large collection of commands, it's actually very difficult to make sure that there are no ambiguities like this, especially when you have things like phrase that can match any sequence of spoken words. And so it's important that for commands which are unambiguous, it still works. And for commands which are ambiguous, it has a set of useful heuristics, which I won't go into, to figure out which command to use. There's another sort of ambiguity, though, that can come up. Let me give you a small demo. Clear word left. Okay, so there's a command called clear word left. What do you think is going to happen if I say clears words lefts, which is clearly not that command? The command is not clear words lefts. It's clear word left. Well, I'm going to bring a little window on screen that shows you what Talon thinks I'm saying, and then I'm going to do that. Clears words lefts. Talon sleep. Just a quick check. Was that window visible? Did people see the window?
Yes,
No?
it was.
It was? Okay,
Yep.
good. All right. So as you can see, Talon heard me say clear word left, even when I clearly said clears words lefts. Focus document. Command mode. Clear line, focus document. And the reason for that is that there's an extra line in this diagram. The command grammar, the set of possible commands, actually doesn't just guide the parser, it guides the speech recognizer, the engine that is actually trying to figure out what the words are I spoke. It will only try to recognize things that it's possible for me to speak as commands. And this is done through a classic trick. You take the command grammar, you turn it into a finite state machine, and you feed it to your speech recognition engine. I don't really know how the speech recognition machine learning black box uses it, but a finite state machine is a pretty simple beast, so it's understandable that it would be useful. But it's a classic result in computer science that if something can be recognized by a finite state machine, then it is actually a regular language. And so in a certain sense, the entire collection of all your Talon commands forms a big regular expression. However, the traditional techniques that have been developed for working with regular expressions do not necessarily apply here because we have some unusual constraints. First off, the regular expression is big. It is all of your Talon commands. There are tens of thousands of these. When you turn it into a finite state machine, it can have millions of nodes. Normally, when we think about matching regular expressions, the regular expression is pretty small, and we want it to be fast. We want the implementation to be fast with respect to the size of the text that we're searching through. But here, the regular expression is huge, and the text that we're searching through is actually a single utterance. It's not going to be longer than a single breath. So this is like a complete inversion of the normal algorithmic situation for this problem. Moreover, this grammar of commands that gets turned into a finite state machine actually gets recompiled frequently because it changes frequently. I haven't shown you this, but Talon is capable of defining commands in a context-specific way, where certain commands are active only in Emacs, for example, or only when you're editing a Python file. And this is straightforwardly useful, but it means that the command grammar is changing all the time. And so this compilation step needs to be fast. If it takes half a second or more, the user will notice when they change their application or what kind of file they're editing. They'll notice a delay when they use a command. And so this really needs to be like 100 milliseconds or lower, or else the user is going to notice. So, these are all pretty weird situations. I mean, speed is nice, but again, speed with respect to the size of the regular expression, that's not normally what we think about when we think about regular expression compilation. So the overall picture that I want to give you here is that Talon has some interesting components which are recognizable from programming language nerds and system nerds like myself. It has a parser generator in it. It has a regex to DFA compiler, but they operate under unusual constraints that actually mean that they can't be implemented in the way you might expect. They need to be implemented differently, and there are interesting algorithmic and design challenges in this. And I think voice control is actually full of problems like this. This is not an unusual thing. I think voice control is full of interesting problems. And part of the point of this talk is to, maybe stimulate some interest in these problems from, smart young people, because currently the bus factor on how to implement a voice control system is pretty small. There are a relatively small number of people that if they disappeared from the earth tomorrow, we would lose the knowledge of how to implement efficient and powerful voice control systems. And as a person who relies on these systems every day, that makes me a little nervous. Um, so enough with how this stuff works. What is voice coding actually like? What makes it difficult? So there are a lot of things, and I won't have time to discuss them all. I'm going to mention a few and then dig into one. So voice control systems have pretty steep learning curves. You might even call them learning cliffs. I estimate that it takes maybe 3 months to get proficient in voice coding. That might be conservative, but for me, that's certainly how long it felt like it took. And I'm almost a year in, and I still don't feel like I'm as efficient as I used to be on a keyboard, but at least it's in sight. Um, so it's not easy, but it is practical. Um, Perhaps the biggest issue, honestly, is voice strain. If you speak to your computer for 8 hours a day, especially in the somewhat unnatural way that voice coding makes you speak, it can put a strain on your voice, and you can end up, um, finding it difficult to speak, finding your vocal cords wearing out. Um, and that's really scary. Being unable to type and unable to speak is a pretty terrible place to be. So this is a really significant problem. Um, Another problem is accessibility APIs. There's various things we'd like to do that involve with our voice commands that involve getting information out of the operating system and into Talon, into your speech control system. And ideally, there would be robust cross-platform accessibility APIs that let us do this. In practice, many of them are not cross-platform, and some of them are kind of poorly designed, and many apps just don't implement them, don't support them. So yeah, this is a pain point. The using accessibility APIs or having to work around their absence. There's also, you have to memorize a lot of voice commands. And even once you've remembered them, it can be hard to stop from forgetting them. So there's various things about how you can design your set of voice commands to be memorable, especially the ones that you use less frequently. That various tips and tricks that have become sort of folklore in the voice control community, like whether you should use verb object order or object verb order, for example. But the thing I'm actually going to dig into in this talk is latency. Because for me, this was sort of the biggest surprise when I came to voice coding. I expected there to be a learning curve. I had been told there would be voice strain. But latency, I should have thought of it, but I didn't. Focus Emacs, switch word fib, slap go bottom. So what do I mean by latency? Let's imagine that we want to get to this line, the line that says print fizzbuzz, and we're all the way down here. If I'm on a keyboard, this is fairly straightforward. I hold the up key. Maybe I overshoot. If I overshoot, it's pretty easy to correct in a single keystroke, and the feedback loop here is very quick. So that's not really a problem. The equivalent of doing this in voice is to use the command north. For me, north goes up a line. Let's try doing the same thing using north. North, 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 north. So as you can see, that was not nearly as fluid an experience. And that's because the latency of a voice command is significantly higher than the latency of a keyboard. Um, Moreover, voice commands get batched. The latency is, voice command doesn't actually execute until you finish speaking. So if you do multiple commands, north, 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 you don't get the immediate feedback that you get from pressing keys multiple times. So, okay, what can we do to improve this situation? Well, one way is we can use repeater commands. So if I say north 7th, for example, that will go north 7 times. North 7th, north. So, okay, that was better, but it still meant that I had to guess how many lines difference there was, and I guessed wrong, and then I needed to correct myself. So it was still multiple round trips, and it was still slower than the keyboard. So what people actually do in practice is they use line numbers. Go 7. And as you can see, that gets you there in one command, and you don't have to wait for feedback. So this is ubiquitous. This is not my idea. This is ubiquitous among voice coders. Um, so the idea here is, well, look, label the things that you need to get to, and then address them by that label. So let's look at another example of this technique for editing regular text rather than programs. Switch word alphabet slap. Let's say I want to change this from Mary had a little sheep, should have been lamb, but I guess it turned into a sheep somewhere. Mary had a little sheep whose fleece was white as snow. I want to change it into Mary had a little goat whose fleece was black as soot. I can do this using relative motion, a relative motion loop, just like the going up and down on the keyboard or saying north south, but instead I'll use go word left and go word right. Clear word right, word black. Clear word right, clear word left, word soot, go word left second. Clear word left, say black. Go word left third. Go word left, clear word left. Run goat, tail. So, okay, apart from some mistakes that were my fault near the beginning, you can see that this works. And in fact, this is how I edit a lot of text. I use shorter commands than go word left and go word right, but the idea is the same. But now let's look at a way of doing this that's much more natural and much faster. North, select line. Draft edit that. Replace each with goat. Left air, select sit through crunch. Say black as soot. Draft submit. So you can see what happened there. Let's make that a little clearer. Draft show. Welcome back. Draft show. Is that I have a little custom editor which gives a label to every word. And we can then refer to those words by label, just like we could refer to lines by number. And this makes manipulating them much easier by voice because I don't have to guess how many words away I am or use a repetitive motion loop to get there. I just name it. Draft hide, focus document. And this is a general pattern in voice user interface design. We have high latency, so we want to minimize our round trips. We want to avoid these interactive navigation loops that work fine for the keyboard, but bad for voice. So we nominalize. We put names on things and let the user refer to those things in voice by the name. We saw examples of this: go to a certain line by its number, select words by their labels. You've also seen me focusing different applications by their name. With a keyboard, you might use Alt-Tab, which again, it's a relative motion move. It cycles through your windows. But with voice, it's much easier just to name the thing you want to go to. Focus Firefox, focus Emacs, focus document. And people also use this for web browsing. There are extensions like Vimium, which label every link on a web page with a small alphanumeric sequence like AD. And then to visit that link, to follow that link, you type FAD. Well, we've seen that typing things with Talon is a breeze. You would just say fine air drum. So this is a very common way to navigate the web using your voice. And the principle behind all of these cases is the same. Put names on things, let the user speak those names. I don't want to make it seem like this is the only way to design around uh, high latency. Another approach is, well, what if it wasn't high latency? Find another input that's low latency. And probably the most commonly used thing here is eye tracking. A lot of people have trouble using their mouse if they suffer from RSI. I'm lucky enough not to suffer from this. But if you do suffer from trouble using your mouse, eye tracking software is actually really good these days. Um, and it has a much lower learning curve than speech control. And so Talon integrates with eye tracking software and hardware, and lets you control your mouse using your eyes. So this is really, those examples that I gave before, I could have done a lot of them using the mouse, selecting things and so on, clicking on links. This can all be done using eye tracking. Another thing you can do is recognize noise. So what do I mean by that? Focus document, focus document, focus Emacs, switch word fib slap, junk slap, go top, search word print. So what just happened there is I issued a search. I searched for the word print. And then to go to the next instance of the search, I used a pop sound. And this sound is useful because it can be recognized at a much lower latency than speech commands. And if you're interested, I can talk about why that is at the end of the talk. It also doesn't use your vocal cords, which is good for voice strain. So this is an example of working around the constraint of high latency rather than working within it. And one of the exciting things about Talon is that it's likely to grow support for more varieties of noise sometime in the future, which I think will help a lot with common things like this that really want low latency. Focus document. So, okay, I've talked a bit about how all this stuff is implemented, and I've talked about what the difficulties of voice control are. Now I want to talk about something near and dear to my heart, which is programming languages. How might the things we've learned affect the design of programming languages? And the first thing I want to do is I want to actually reframe the question. Rather than talking about uh, programming languages, I want to talk about all of the stuff that sits between us and a program. So when I think about programming languages, I think about syntax and semantics. But you also have an editor, a compiler, you have maybe your build system, your IDE, right? So I'm going to call all of that stuff the programming system or the programming environment. So, okay, what can we do in programming systems or environments to address voice coding? So I'm just going to focus on the issue of latency since I've already talked about it. One thing we can do, the obvious thing is we want fewer round trips. So don't make me do things that could just be done for me automatically. Don't make me context switch. Don't make me switch to a terminal, run make, look at the output of make, find the errors, switch back to my editor, go to the errors on those lines. If I'm using a keyboard, I can do that reasonably fast. But even using a keyboard, this is inconvenient. And when every switch between applications requires you to wait, this is horrible. So we really want live programming environments. And this is, of course, not a new idea, not an idea specific to voice coding, but it is really useful for voice coding to have things that update live, that don't require an explicit action to be taken, and especially not an action that could involve, you waiting for the computer to react to it for you to know what you need to do next. Just update the compilation results live. Show me where the errors are immediately. Another thing you can do is we've already talked about nominalization, about how adding labels to things makes them easier to refer to in voice commands. Well, we already name things in our programs. We name them, we put names on functions, we put names on variables. What would be nice is if we could expose those names to our editor, or rather to our voice control system. And so I'm now going to be showing a demo of research by Berger, who I think is even present right now. And I believe this is work that he's done for his master's thesis research of integrating Talon with something that's aware of the program being edited. Focus terminal. North. Let me just double check that the program audio is going to be, aha, share computer sound. Okay, please let me know if you can't hear this, as that means something has gone wrong. I'm now going to play the video. Say that we're editing some file, and we think there's a problem with the update function. First of all, we need to find the update function. So, go fun update. Okay, now that I can see it, I notice that the problem is that it's updating the model in increments of 3 instead of in increments of 1. So, go number. What that did was it jumped to the nearest AST node that was a literal number, which in this case is our target. So now let's fix it. Deli sit 1. And while we're here, we notice that the update function is missing a type signature. So let's go add that. North second slap word update of type message to model to model. And as you can see, it actually knows about the names we've given our types because it picked up that message is spelled MESG. Focus document. So I think this is really cool work. I think this is going to make voice coding a lot easier if we can get it working reliably across different editors and different languages. And yeah, I think this is a real game changer. So, all right, but I'm not done yet. What else can we do to address high latency? One option is we can have quick access to the unfinished parts of a program, right? And this leads to what's called hole-oriented editing. So this is where your program is regarded as having holes in it, which are the parts that you haven't completed yet, or that might have type errors or other problems. And if you have this problem, if you have this, representation, right, it actually leads to a much smoother experience for voice editing. So I'm going to play a short demo of a tool, of a programming environment called Hazel. You can find it at hazel.org, that is built on this idea and several other interesting ideas. And I want to emphasize, Hazel was not designed with voice editing in mind. It is a fortuitous accident that this works anywhere near as well as it does. Focus terminal. Pit space dashing demo Hazel, tab. Slap. This is a demo of the Hazel programming environment combined with Talon voice control. Let. Word fib of type integer arrow integer. Tab, lambda. Near tab. Case. Near tab 0 tab 1. Slap 1 tab 1. Slap under tab. Word fib apply near -1. Right plus word fib apply near -2. Tab word fib space 4. Here are all the things I didn't have to worry about as I was writing this code. I didn't have to worry about balancing my curly braces. I didn't have to worry about inserting equal signs or pipes in the right place. I didn't have to worry about indenting my lines or about re-indenting them and reformatting them if the lines got too long. I didn't have to count characters to move the cursor to where I wanted it to be when I wanted to add some more code. I just hit tab, and it moved to the next hole. I didn't have to worry about compiling my code, or even running it. As you can see, the result is right here. And if I change the code, it will rerun it for me. Junk 5, junk 6. As a kicker, here is all the code that I needed to write to integrate Talon with Hazel. Focus Emacs. That's the whole thing. Focus document. So yeah, Hazel is pretty cool and works like really surprisingly well with voice editing with only a minimum of effort. And I think honestly, right, I've introduced Hazel as, a whole-oriented editor, and this is true, but it has the potential to integrate all of these ideas. You saw that it updated the result live when I changed the code. Um, it's also, Hazel is a rethink of the entire, compiler editor stack. And so one of its goals is to expose more information about your program to your editor, and possibly, therefore, also to Talon or to your voice control system of choice. So, in the next 10 years, we might be able to get all of these things working in Hazel. Um, uh, yeah, Hazel might be, the language for voice editing. The only problem, of course, being, they're trying to reinvent the world. So if you want to integrate your program with, other languages or, yeah, like there's a whole lot of work to be done on Hazel. Reinventing the world is hard work. So that was a lot of demos that I just threw at you. um, Here are, the things I'd like you to take away from this talk. First off, I haven't explicitly talked about this. Voice coding is hard, right? I've mentioned that, but it is practical. And if you can't type for whatever reason, it can be a lifesaver. So hopefully you've come away convinced that, if you didn't previously realize voice coding was a serious option, it is, right? It really is. But besides that, even as a researcher, voice control is full of interesting technical problems to be solved or just to be documented, just to be like explained, like what are the trade-offs here? Why do we need to do this instead of that? Um, uh, I also think that from the design side, from the design of the side of trying to design a voice interface for expert users, for example, for programmers, voice interface for expert users has a lot of unique challenges. I've mentioned latency. I've mentioned some other ones very briefly. And because of those challenges, it has its own unique design idioms, right? The one that I foregrounded was nominalization, right? Naming things, right? Um, and I think both of these sides, the technical problems of implementing voice control systems and the problem of designing voice interfaces can be fruitfully viewed through the lens of programming systems design. Um, and I hope I've given you some examples of that. All right. So that's nearly everything. I just have some links that I'd like to throw up on screen. Focus Emacs, switch word links, slap. Yeah, so here's the link to Talon Voice, to the Talon voice control system, which is the system I've been using throughout this entire talk. It's really cool. You should go check it out. Oops. Here's the link to Hazel, the programming environment I showed off at the end. Here's the link to Gauterberger's integration tool that integrates Talon with Tree Sitter, which is a thing that sort of parses your program and understands things about it. You can find me at ernst.net. I have some stuff about my experience with Talon at ernst.net/Talon. And yeah, I'm going to stop and allow questions just as soon as I turn recording off.